Hi, in this video we're going to be looking at bond energies. So the net energy charge for reaction is called the heat of reaction or the changing enthalpy, which is delta H. There are two ways to solve for delta H, and today we're going to look at the first way, which is using bond energies. So let's take a look over here. When you're breaking bonds apart, your changing energy will be positive. When the bonds are being formed, your changing energy will be negative. That is the main thing to know over here. So as you can see, breaking bonds is endothermic because energy is absorbed, like we see over here. And then when bonds are being formed, it's going to be exothermic because the energy is released. Alright, now let's look at some practice problems. You're always going to be given with the bond energies to work with. Now determine the enthalpy change. Alright, let me quickly show you how to find enthalpy change. It is always going to be the sum of the sum of reactants minus the sum of products. Alright, this is for bond energies. When we're working with bond energies, we do reactants minus products, and the reactants, you'll be finding them by using the numbers over here, and same goes for products. So let's see. First problem, it says determine the enthalpy change, which is delta H reaction, that occurs when two gaseous oxygen atoms combine to form a gaseous oxygen molecule, using the table of average bond energies. So how would our two oxygen atoms bond? Well, oxygen bond with a double bond, as we should know already. And this is how it works. Alright, this is a double bonding between O and O, and we will not look at any of the stuff on the side because we're looking at bond energies. So we'll only be looking at the bond. And this is a double O and O bond, which means the bond strength will be 499. And see over here, we learned that when bonds are formed, there is a negative energy change. Therefore, our 499 will have to turn into negative 499. Negative 499 kilojoules. And this is because bond is being formed, energy is released. 499 kJ released. As you should remember from a few units ago, the word released means a negative value. So the answer is negative 499 kJ, but it's actually meaning 499 kJ being released. Number 2, using only the information from the thermochemistry equation, make a comparison between the sum of the bond enthalpies in the reactants to the products. Alright, so CH4 is, we first need to draw all the Lewis structures. H. We don't care about anything else but the bonding, so we can ignore all of those. Double bond times 2. CO2 is double O bond. And then H2O is H double H bonds times 2. So let's see, what is CH4? CH is 412. So reactants is 412 times, we have 4 of those, 1, 2, 3, 4, plus our O2 times 2. So 2 double O bonds, which is 499 times 2, which is equal to 412 times 4 plus 499 times 2, which is 2646. Our products have, let's see, CO2, which is two double C bonds, which will be CO bond 799 times 2, plus OH bonds times 4 because there's 2 in each H2O. So OH 467 times 4, which will be 799 times 2 plus 467 times 4, 3466. Now, one is 2646, the other is 3466. Now, why is one value then greater? Why is our enthalpy, when there are sum of bond enthalpies in products, is greater than that of in reactants? Well, let's take a look over here. Right? Because our delta H reaction is negative, it means it is exothermic, right? Negative changing energy means it is formed, and formed bonds means it's exothermic. Now, negative delta H means it's exothermic. Now, an exothermic releases energy, and energy released when bonds are being formed. These are the bonds that are being formed by our reactants. If we reverse the reaction, these will be the bonds that are being formed. But in this case, these ones are the bonds that are being broken apart, and that means these absorb energy and these release. Since the overall energy is released, that means our energy in products will be greater than our energy in reactants. Now next we need to use the chemical equation below and the table of average bond energies to answer the following questions. Draw the Lewis structure for every single species. Alright, N2, N you should know is that the triple bond. It's always triple bond. Triple bond N. H is always a double bond, is a single bond times 3. And the product will be NH3. N single 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 H H H. And this is how you draw the Lewis structure for the 3 of these. Now part B, calculate enthalpy change. Alright, great. Enthalpy change is reactants minus products. So what is H bond? H dash is 436. 436 times 3 plus single and triple N bond, which is 941. 941 minus our product, which is H dash N bonds times 3. H dash N, which is 393 times 3. 393 times 3. And let's see what this will give us. 436 times 3 plus 941 minus 393 times 3. We get 1070 kJ per mole. Oh, sorry. Since there are 2 moles of NH3, there are actually 6 393 bonds, 6 HN bonds. So this will change up our answer a little bit. And we'll instead get negative 109 kJ per mole. This is the correct answer because I forgot to take the times 2 into account. Now draw a symbolic relationship that demonstrates the flow of energy. Well, this is negative. Negative means what? Negative means it's exothermic. So let's quickly draw a system and surroundings. And flow of energy is this way. That's it. We have system, energy going out into surroundings. Number 4, using the thermochemical equation for the combustion of methane and the tables of average bond energies to find the average bond energy for CH bond. Alright, let's see if we're given CH bond first. We're given CH bond, alright. But it wants us to find using the equation. Alright, so let's see. Now let's assume we're not given the CH bond, alright? We're not given this bond. And how do we solve for it when we're given everything else? And here, let's draw this again real quick. C, H, 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 H. And this is O double bond O. This is C double bond O double bond O. And you do not necessarily need to draw all the lone pairs and all the other electrons because we're only looking at the bonds. And this is H, H, and O times 2. This also times 2. So the way this will work is, since the change of energy is equal to our reactants minus products, we can set up an equation. Alright, negative 802.23.3 is equal to products. What is products? No, is equal to reactants minus products. What is reactant? CH bond. Oops, we don't know the CH bond is, so this is what we're looking for, right? How much CH bonds are there? 4. So let's use the variable x. 4x. Now let's put everything else in. OO bonds. So what is the OO bond? It's gonna be 499. 499 plus 499 times 2 minus C double O bond, which is 799 times 2. Plus H dash O bond, which will be 467. And we have 4 of those. Alright, now let's quickly solve this. Negative 802.3 is going to be equal to 4x plus 499 times 2, which is 998, minus 799 times 2 plus 467 times 4 is equal to 3466. And this is going to be subtracting 3466. 3466. So now we have 802.3. Oh, wait, now just do the math. Negative 802.3 minus 998 plus 3466 equals 4x is equal to 1665.7. So divide that by 4 and we get x is equal to 416 kJ per mole. So let's double check. Is our X equal to 416? Close enough, 412. And again, the bond that we find will not be 100%, may not be 100% accurate because this is using average bond energies. Some might be greater, some might be less. Number 5, draw Lewis structures for all 4 species represented in the reaction bond. That's easy. C3H4. Alright. So let's say C double bond, C double bond, C, each with an extended leg of H. And let's see, the octets are all completed, and this is the right one. O2 will be double bond O, as we learned, times 4. And then CO2 will be C double bond O times 3. And H double OH bonds times 2. Alright, calculate the enthalpy change that occurs in the reaction. Okay, so this is basically doing what we've done again. So CH, we have 4 C-H bonds. C-H, which is 412, energy of 412. 412 times 4 plus C double C bond times 2, 612 times 2, 612 times 2 minus, nope, sorry, plus. We still got to add more. Add O double O times 4, which is 499 times 4. 99 times 4 minus O double C times 3 times 6 actually. C double O, 799 times 6, because there are 6 of these bonds. 799 times 6 plus OH times 4, 4 of those. 467 times 4. 467 times 4. And this will be 412 times 4 plus 612 times 2 plus 499 times 4 minus 799 times 6 plus 467 times 4. And we'll get an answer of negative 1794, which is approximately equal to 1790 kJ per mole. And that is our answer. Number 6, use the chemical equation. Alright, same thing as above. Draw the Lewis structure for all of them. So C double bond C, single bond H. Oops. This one is drawn a little bit differently. This is C2H2. So triple bond. We're gonna need a triple bond over here and a single bond over here. That's good. Times 2 plus O2 times 5, and then CO2 is C double O times 4, and H2O times 2. So same thing as above. We have a C-H bond, which is 412 times 2 of those. 412 times 2 plus a C triple C bond, which is 960 times 1 of that, plus O double O times 5, which is 499 times 5. Subtract by O double C times 4, O double C 799. Actually, I think it'll be times 8 because there's 2 in each of them. Yep. 799 times 8 plus O single H, which is 467 times 4. 467 times 4. So let's see. 412 times 2 plus 960. 412 plus times 2 plus 960 plus 499 times 5 minus 799 times 8 plus 467 times 4. Oops, sorry, there's 2 of this. So actually this will be times 4, and this will be times 2. Sorry, so this will be 412 times 4 plus 960 times 2 plus 499 times 5 minus 799 times 8 plus 467 times 4. That will give us an answer of negative 2197, which is approximately negative 2.20 times 10 to the 3rd power. And yeah, just make sure that when you're cutting bonds, you take the coefficient, the number of moles into account. Number 7, the following question pertain to the bonds between the carbon atoms in C2H6 and C2H4. Draw the visual relationships that show the relative bond lengths. So we have a C and C bond and a C double bond, right? So this one, C, is gonna have 3 H's all attached to it, and it's gonna have a long single bond C with 3 attached to it, because we need to show the relative differences in bond length. And why? It's because it's a single bond over here. On the other hand, C2H4 is gonna have a double bond in between which is why this bond is going to be shorter. So when it tells you to draw the relative lengths, just make sure that you show the single bonds are longer than the double bonds, which will be longer than the triple bonds if there are any. Which carbon-carbon bond contains the least amount of potential energy? Alright, let's type real quick. The answer is going to be C2H4, because potential energy decreases as bond length increases. That is because VE, valence electrons, are closer to nucleus of another atom. And C2H4 has the shorter bond length. Now, which carbon atom requires the greatest input energy in order to be broken? And again, it is going to be C2H4, because more energy is required to break shorter bonds. C2H4 has a shorter bond length than C2H6 due to the double bond. And that is it to every single question on our bond energies practice problem. Thank you for watching.